Okay, so one little aside that I wanted to bring up at this point because it's something you see a lot, um, and it's useful experimentally, is the isotope effect, right? Where the changing the isotope of a molecule, atoms in a molecule, will change the frequency of stretches and bends. And this depends upon this formula. So hopefully you've all seen this formula before, where the vibrational frequency nu is equal to 1 over 2 pi times square root of k, which is the force constant, spring constant, divided by mu, which is the reduced mass, right? And so atoms that have isotope effect, heavier atoms will give rise to lower frequency because this is in the denominator. And K is staying basically the same when you change the to a different isotope. Why is that? Because if you change the neutrons, right, in an atom, you're not changing the electrons, and electrons are what are participating in bonding. So K stays basically the same across different isotopes, but mu is changing. Mu increases with heavier isotopes, giving rise to a lower nu or frequency. Only the atoms that move in a normal mode will be the ones that give rise to an isotope effect. So, for example, the A1 normal mode, that was a symmetric stretch, okay? And if you have a symmetric stretch, let's look at that symmetric stretch. There it is, okay? Look what's moving. The hydrogen's moving. Carbon's staying the same, right? Carbon is not moving. So if you look at CD4 instead of regular methane, you will have a pronounced isotope effect. The symmetric stretch in CD4 will be significantly lower because deuterium is significantly higher in mass than CH4. However, if you make a C13 methane instead of C12 methane, majority C12 at least, natural abundance, you will not see an isotope effect for the A1 normal mode because, again, that carbon isn't moving here, okay? Kind of makes sense. How can an atom contribute to stretching frequency if it's not moving, right? All right, so now let's go back to the problem at hand, which was looking at normal modes of methane. And we found that there were 4 sort of sets of normal modes, but 9 modes total, right? If we count degeneracies, those were A1 plus E plus 2T2. So which ones are IR active? Well, you look at which ones have the same symmetry as the transition moment operator. And remember, that's for IR spectroscopy is X vector, Y vector, and Z vector. All of these modes are transform as T2. And so only the two T2 modes are going to be IR active. That's what it tells you. A1 mode, not going to appear. That is silent. E mode is going to be IR silent as well. So you won't get a peak for the E mode. Okay, you won't get a peak for the A1 mode, but you will get 2 peaks at 2 different energies for the 2 T2 modes. That was an asymmetric bend, and the other one was an asymmetric stretch. Okay. All right. So now we can talk a little bit about. Let's actually stop here for this video.